All right, some other identities that we would like to discuss involves what we call the even and I identities, right? We talked about even and I functions before, and what we want to do is we want to talk about them again. Um, from our earlier math studies, right, what we found was in order to determine if a function was even or odd, we could evaluate the function at a negative x value, right? Whether we're talking about even or odd. If the function was even, we said that we'd end up with the exact same function that we started with, right? And so an example that we used was f of x equals x squared, right? If I plug in negative x, when I square it, I'm just going to get the same thing that I would start with, x squared, right? And so that means that this would be an even function, right? If we have an odd function, we end up with the opposite of what we started with when we input the negative, right? And so one of our examples was f of x equals x cubed. If we plug in negative x, when I multiply negative 1 3 times, it's going to be a negative. And so it's almost like taking that x and cubing it and making it a negative, right? And so we have our trig functions. We can test whether they're even, odd, or neither by using the exact same things, right? For instance, one of the things that you should note is that I know this may be hard to see, right? But one of the points that this is my y equals sine of x. Remember, sine goes through the origin, right? So we have y equals sine of x here. And if I want to find out if it's even or odd, I can do the same f of negative x equals f of x, right? One way to do it is graphically, because we have our trig functions. It's a little weird, right? Doing it algebraically may be a little difficult to think about. So I have the graphs here, right? And I'm just going to look at a couple of points, for instance. If I look, this point right here is pi over 2, 1. This point right here is negative pi over 2, negative 1, right? So that means, hey, if I plug in negative pi over 2, if I get exactly the same thing that I started with, if I were to plug in f of pi over 2, then I could say that it's even. If I get the opposite of what I get when I plug in a positive pi over 2, I would say that it's odd. And if I look there, f of pi over 2 is 1, and f of negative pi over 2 is negative 1. So I don't have the even case. I actually have what we call the odd case, right? Now, this is not, you shouldn't just use one example to do this, because it has to work for all x where the function is defined, right? So sitting here, this symbol right here means for all. For all x where your function is defined. Now, I just looked at this one example, pi over 2, but as you can kind of see, if I chose like the point pi over 4 and negative pi over 4, I'd get the same type of situation. If I chose 3 pi over 2, you can't see it on the graph, but negative 3 pi over 2, I have a y value of 1. I get the exact same thing. So my sine function is odd. Another way for you to tell that is to see if that function is symmetric with respect to the origin. Meaning, one way that I talked about this in class is that, and I think it's probably the easiest for me, is to say that, hey, if I reflected my graph about the x-axis and the y-axis, then will I end up like, so let's say I did this part of my graph, reflected about the x-axis, then the y-axis, would I end up with this other part that's on the left side of my y-axis? And that is the case, okay? We have our function y equals cosine of x here. And as you can see, we're going to determine if it's even, odd, or neither. If it's even, when I plug in a value, the opposite of a value, I should get the same thing as if I plugged in the positive of that value. And if it's odd, I'll get the opposite, right? And so if I plug in, let's say, pi, I should get the exact same thing as I plug in negative pi. If that's the case, then I would be even. And as you can see, when I plug in pi, I get negative 1. Plug in pi, I get negative 1. And so I have f of negative pi equals f of pi, right? They both equal negative 1, right? At pi over 2 and negative pi over 2, that same exact thing happens. And at all points, that actually is going to happen. So your cosine function is actually even, okay? And even functions are symmetric with respect to the y-axis. So as you can see, my function is symmetric with respect to the y-axis, right? This is origin symmetry. All right, and last but not least, our tangent function, if you look at that, that is also an odd function, okay? And you can see in these 2 points here, I plug in the power of 4, I get 1. I plug in negative power of 4, I get the opposite of what I get when I plug in power of 4. So that is an example. Of course, we want this to work for all x, and you'll see that this is odd as well. And it looks sort of like f of x equals x cubed, right? It's symmetric with respect to the origin. And so not only is sine and tangent odd, their reciprocals are too. So tangent, cotangent, sine, and cosecant are all odd, and cosine and secant are all even. Let's look at some examples where we use this. Example 5, determine whether the function is even, odd, or neither. We have f of x equals 2 times the sine x cosine x, right? Remember, if I want to determine if it's odd, right, I'm going to plug even, odd, or neither. I'm going to plug in negative x. Well, I already know that my sine function is odd, right? And so I know that when I plug in negative x for my sine function, I'm going to have a negative sine of x. And since my cosine function is even, I know that when I plug in that negative x, I get the same thing, right? So it's the same thing as cosine of x. And so this equals negative 2 times sine x cosine x. This is the opposite of what we started with, and so we have odd. Okay? Example 6, use identities to simplify the expression, right? I have sine cubed of negative theta over sine cubed theta minus sine theta, okay? So one of the things about identities is that the angles have to all be the same in order for me to simplify like the overall thing, you know what I'm saying? And so one of the things I'm going to do is I'm going to use my even and odd properties to get rid of this negative sine cubed negative theta here. Since I know that this is a odd function, and when I plug in the negative is the opposite of what I get when I plug in the positive, I'm going to write this as negative sine theta cubed over sine cubed theta minus sine of theta. And notice when I cube something, I multiply it 3 times. That's an odd number, and so that negative is just going to stay negative. So this is the same thing as negative sine cubed theta. You probably didn't have to do that in multiple steps and write it the way I did, but I did, okay? And so now I want to simplify this. Now there is no identity with something to the third power, so we're going to have to do some other things. All right. If I look in my denominator, both of those terms are sine, right? And so what I naturally think is, well, let me factor out a sine, because all of these expressions have a sine in it. And when I factor it out, I'm going to get a sine squared minus 1 left. And now that I have this sine factored out, I can cancel it with one of these 3 sines multiplied together on top. And so I'm going to get negative sine squared theta over sine squared theta minus 1. Now what I don't want you to do is think that you can cancel those sine squares of theta, right? Because that's a minus 1 in the denominator, right? So I can't cancel anything. I got to work in the numerator and the denominator. If I look here, this fits my Pythagorean identity, right? The only difference is if I subtract sine squared from both sides, I get cosine squared of theta equals 1 minus sine squared of theta, right? And so I could rewrite this as a negative sine squared of theta on the numerator, and I can write that as a cosine squared of theta in my denominator. And if I use my quotient identity, I know that sine squared over cosine, or sine theta over cosine theta, equals tangent theta, so this would be a negative tangent squared of theta, right? Usually when we simplify these things and I have a single, I want to end up with a single expression, and that's what I've ended up with here, okay? All right, and so that's the end of what we're going to do in this section. We will do a review and continue next time.